look at this handout. Okay, importantly at the beginning we're going to be looking at alkene reactions. Okay, and with the pi bond, we're going to have lots of reactions other than acid-base, transformations, chemical reactivity. And an underlying idea with the reactions is understanding thermodynamics and kinetics. And this looks at that with particular focus on organic chemistry. Here we go. There's just some standard line reactions. And this is thermodynamics. Teaser questions. For example, if you take NF3, it'll decompose into nitrogen and fluorine. Or at least that's a possible reaction. Now you can balance this, which I have done that. There's some bond strengths given down here. And we can ask certain questions about these reactions. Which reaction above between either the fluorine NF3 or Ni3, which gives off the most heat / energy? As it says, here's your chance to use your calculator. Your one and only chance in organic chemistry to use your calculator. My calculator collection is growing. Doing an expensive one here. Am I missing a calculator? Which reaction above is endothermic? NF3 or Ni3? Which reaction will occur fastest? Are the reactions driven by entropy or not? These are some example questions that focus on thermodynamics and kinetics. Anybody get the answers to these? Could you all answer these if given a few minutes? I suspect we should look at how to do this. Next page. Some introductory material. First off, the idea of line reactions. Line reactions is where we show reactants such as this alkene plus HBr, and then a reaction arrow, and then products. Okay? This is a line reaction. This plus this yields this. Sort of what this means, yeah? You can see line reactions different ways, different information. For example, maybe the HBr is put on the line. This is this alkene reacting with HBr, yields this. We can also put maybe on the line some reaction information such as temperature and maybe time. Okay? So this is just the general idea of a line reaction. A line reaction may also show multiple steps. Take this alkene, react it with HBr. Okay, that's one step. And then come back and react it with sodium cyanide. Now, this assumes that this reacts with HBr to give something new, and then that something new then reacts with sodium cyanide to give this. So this is really two different line reactions sort of shown together. You guys typically, whenever you see this, you guys want to mix these two. These two are not mixed. This is done 1 week, your product's purified, and in the next week you do this. They're not together. Okay? But this is just a multi-step line reaction. Now if the 1 and 2 was not there, that means all this is mixed together. Okay. So thermodynamics. This is just my version of what it's all about. You know all this, you've seen it all. We can sum that up with our free Gibbs energy equation, delta G equals delta H minus T delta S. Okay? And delta H would be, what's that term? That's your enthalpy or heat. Okay? Temperature, what is delta S? That would be entropy, or so-called randomness. Not much new there. Of course, which is favored? Delta H Negative delta H tells you it's a favorable reaction because the products have lost heat energy. Thus, that's exothermic. Exothermic, typically a favored reaction. That would be where the reaction has a negative delta H, right? Entropy, on the other hand, positive delta S is favored, where the products have gained disorder. That's like a double negative, it looks like. They've gained disorder, or you can say they've lost order, you know, as opposed to losing disorder. Basically, you got to get what these terms mean. Let's look at some examples of entropy. Now, entropy we will not do any calculations with. Okay, we will assess it sort of qualitatively. For example, we take this alkene reacting with HBr, we can get this, what do you want to call that, 2-bromopropane. We would predict that delta S is negative, which means the system has lost disorder. Does that make sense? Well, look at this. Two molecules are reacting to become one molecule. So what is that doing in terms of order? Two molecules are coming together to make one. That's ordering. So in terms of disorder, has it increased in disorder? No, we're dealing with double negatives here, right? It's actually lost disorder because it has gained order. And it's lost disorder, delta S is negative. Okay? This is all this, okay, negative disorder. You got to get it straight. So we would assume or predict that delta S is negative. On the other hand, if you look at the reverse reaction, I could show this going this way, or I could just turn it around and say, hey, if we start with this, and this thing decomposes, then we say one molecule is going to two, so it's gaining disorder. And if it's gaining disorder, delta S is positive. So which way is favored? Based on entropy. Is A favored or B? B is just the reverse of A. B is favored based on entropy. But there's another term in the delta G. There's also enthalpy. Now, is it favored? Well, there we will actually calculate. What if one is favored and one's not? Well, then overall it can become a little difficult. What if both are favored? Well, then delta G is going to be favored. About C. This is just where this compound makes this ring. Would delta S be positive or negative down here? Negative. Negative means
it's losing disorder.
it's losing disorder. Is it losing disorder?
Yes.
Why do you say it's losing disorder?
Because it's making
The ring is more
favorite like it wants to. Well,
So why is it more favored?
because it rings eight.
So you're talking about enthalpy?
I think. I don't know.
Okay. We're looking at entropy though. Delta S. Is delta S going to be positive or negative? You can't tell me delta S is going to be negative because enthalpy is favored. And that's a different term. Right? Entropy, order. Is it becoming more ordered or less? What if I can flap my arms around? Okay, now I've made a ring. I can't flap my arms around as much. It's more ordered. It's more ordered in a ring. It has less of this possible movement. Since it's more ordered, delta S is going to be negative. Yes. you were
Yeah,
right.
I said, I was like,
Good job, you were right. Okay, so there's some examples. System becoming more ordered or less ordered. Delta H. Delta H, on the other hand, we will actually quantify or calculate. Okay? This is where we're going to use our calculator. Look at this reaction. This is an alkene, very similar to above, except I got one less carbon. And I drew it out fully. This alkene reacts with HBr to give this. By the way, what type of reaction is this? You know, there's only about 5 or 6 types of reactions in chemistry.
Synthesis?
What type is this? Addition reaction. HBr is adding to this. HBr has been added. It's an addition reaction. We will do plenty of different types of addition reactions for test 2. One type is an alkene reaction with HX, or hydrohalic acid, to give an alkyl halide. Alkene is now an alkyl halide. It's now an alkane with a bromine. Okay. Can we calculate delta H for this? Delta H is calculated using bond strengths. We look at what is broken versus what's formed. The pi bond is broken. Everybody agree? There's no pi bond. How much is a pi bond worth? If we look at the table in the front, now some tables get pi bonds differently. These numbers I don't think are in the table. On the front, it gives a pi. It looks like a pi bond 174. Unfortunately, I think that's for the entire bonding between the carbons. That's pi bond and signal bond. Okay. I'm not showing you where I got these numbers from. Tables will be clear when you're asked to use them. Okay. But somewhere I got a number that the carbon-carbon pi bonds were 63 kcal per mole. Some table, not on this table. What else is broken here? The HBr bond is broken. Oh, it's no longer there. That's 87 kcal per mole. That's probably on that. Is there an HBr? Yeah. See on the very front table it says HBr 87. That one is on the table. What's broken is here, and it adds up to 150 kcal per mole. What is formed? Does everybody agree that a carbon-bromine bond is formed? CBr. I got 69 here. Is that in the front table? Look in the front table on the bottom right side. It's got a carbon-bromine bond with the different carbons having different substitution. One of the bromines is on a methyl, the other is on a primary carbon, secondary carbon, and then tertiary carbon. What do we have here? The bromine is on what type of carbon? That's a primary carbon, right? Because it's bonded to one other carbon. And according to this table, bromine on a primary carbon is 72 kcal per mole. Well, apparently I used a table that had 69. I know that could be confusing, so let's write. Okay. Sometimes different tables give you different numbers. I think when I did this example, I was using a different table. A CH. Does everybody agree that we've also made a new CH bond? That's what we made here. And the carbon is primary. And if you look on the front, what value is the table? Does the table give for a primary CH? Is it 101 or is it different? Primary CH. A methyl H is not a primary CH because a methyl is not considered primary. It's 101, yeah? Yeah? Okay. So this is what's formed. This adds up to 170. Okay? 150 versus 170. The difference in these two is 20. Okay? That's going to be your delta H. But is it positive 20 or negative 20?
It is positive.
Positive 20 or negative 20? Looks to me like it'd be negative 20. What's this negative 20?
Yeah.
Is that a hand raise? Which side's more stable? These are bond strings. Which side's got the stronger bonds?
Products.
This is a, what do we have over here? Pi bond, sigma bond. What did we make over here? We made 2 sigma. Over here we have pi and a sigma, over there we have 2 sigma. Which is stronger bonds? Pi and a sigma or 2 sigmas? 2 sigmas, right? These are stronger bonds. And if you see that here, that's why this number is higher, because these are bond strengths. Stronger bonds. Okay? Stronger bonds means more stable bonds. More stable bonds means lower energy bonds. These bonds are lower in energy. They're stronger. By how much are they lower? 20. They're 20 lower. Delta H equals negative 20 kcal per mole. Negative 20 means exothermic or exothermic. But it means energy is released. Why is energy released? Because we form more stable bonds. Those bonds are more relaxed, they're more stable, they're lower in energy. This is higher energy bond. When you form the lower energy bonds, you give off heat, you give off this much. The system loses this much. Okay. Now I think you can get the answer by taking reactants minus products. I'm not even sure which is which. I'm sure you're probably taller than Gen Chem. Reactants minus products? 150 was reactants. Reactants minus products. Okay, there you go. But if that's all you know, you're gypping yourself. Please understand what the numbers mean. And I tried to go through what the numbers mean. That reaction gives off heat. It's exothermic. So is it favored by delta H? Let's go back and look at that. Is this reaction favored by enthalpy? Yes. It's negative. It's exothermic. It's favored by enthalpy. Is this reaction favored by entropy? No. 2 molecules going to 1. So one term is favorable, the other is not. That makes you kind of question, is delta G going to be favored overall? And it would be difficult to assess for what we're going to be doing. Let me ask you this. When we get to kinetics or something, or rates, if this reaction is slow, would you want to heat it? Typically heating maybe speeds up reaction, but would you just want to heat it at some huge high temperature? Why would it go back?
Well, because it lost energy to get there, but it's going to go back and the particles from dust.
Not necessarily. I mean, carbon reacts with oxygen exothermically. But if you then turn around and heat, well, that doesn't work. Possibly. Would you want to heat this reaction? Here's what I'm getting at. Which term does heat influence? Which term does temperature influence?
Entropy, sorry.
T delta S, entropy. It magnifies entropy. Is entropy favored here? No. It's not favored. Temperature magnifies entropy. If you magnify a non-favorable term, is that going to help your reaction? No. You got to be careful about heating this reaction too much. You're going to make entropy. You're going to make it. Okay. What I'm getting is, do you understand delta G equation and fully what it means in the practical world? Okay. You can calculate. Here's another reaction, and this is giving you room to calculate. Delta reaction is exothermic or endothermic. You've got this alkane reacting with fluorine to give this product plus HF. Okay? Calculate delta H. These bond strengths should be in the table on the front. Please have that done by Friday. Now if you go back, please also have these answered by Friday. That is, which reaction above gives off the most heat? How would you do that? Heat is delta H. Can you calculate delta H for each reaction? Okay. You do need to have it balanced. In the reactions we did, it was every coefficient was 1, 1, 1. But if you have one coefficient being 2, that means double the bonds are being broken or whatnot. Okay? Which reaction is endothermic? Well, that's just going to come from your calculations, right? Which reaction will occur fastest? Is that entropy or is that thermodynamics or kinetics? This is kinetics, right? Has nothing to do with entropy. Or not directly. 4 you should be able to answer. Are the reactions driven by entropy or not? Okay. Please have those looked at. You should. 3 out of 4, I think, are pretty straightforward. The one about rate we really didn't cover. We'll look at kinetics in the back portion of that handout. Before we dismiss, any last questions? Test on Wednesday. Last questions? Did we? Any questions about the test? Okay, guys, have a good day. So, right after physics,
And then, but then,
Right after I will try to be there.
看我。